All right, we're going to do a couple more. They're going to get a little bit harder as we go. Our first bobsleigh question here. What I'd like you to start doing as we get into questions that are a little bit trickier is draw a free body diagram. So for our bobsleigh, we've got gravity pulling it down. There's always going to be gravity. We've got a normal force pushing it up. The normal force is the reaction of gravity. So normal pulling it down into the ground. The ground reacts and pushes back up on the bobsleigh. That reaction force that's upward, we call that the normal force. We'll talk about that more, but just for now we'll call that F normal. This particular question says you're pushing it with a force of 510 and there is no friction. The force that you push with, we're going to call that the applied force. In this question, it's equal to 510. If we cared, we could figure out gravity. It's mass times 9.8. For this particular question, we don't really need it, so I'm not gonna get it. Now that we've got a free body diagram, we can jump into F net equals ma. Because there's only one force, that is our F net. This is kind of similar to the last couple questions. We're going to build on it. This is similar to how we did the lab. There only was one force, so we can say 510 equals 170 times A. Divide the 170 over, you're going to get that the A is exactly 3, and through the magic of Newton's second law, meters per second squared is the unit. Now, the point of this one, and bumping it up a level with the next one, why is it important that the bobsleigh was on ice? How would this question change if there was friction? Think about it, and I'm going to scroll down and we'll tackle the next one. If there's friction, it complicates our free body diagram a little bit. We've still got gravity straight down. Still don't really care how big gravity is. It's going to be the mass times 9.8. We've still got the reaction force of the ground pushing back up on it. That's called the normal force, or Fn for short. In theory, those should be the same length. I don't know if I made it perfectly well, but I'm close. We've got the forward force. I'm going to call that F applied. The number is 510 for that one. If we're not on ice anymore, we're going to have some backwards friction. I'm going to call that FF for friction, and the numbers that were made up for this one, the friction value is 127.5. Now this goes back to all the practicing we did last week. If we've got forces in opposite directions, we have to, it's a vector addition, but it turns into subtraction to figure out what F net is. Newton's second law is, we always know F net equals ma. The 510 is going to win this tug of war, so I'm going to make it the positive force. So F applied as the forward, subtracting friction because it's in the backwards direction. That's our F net, and that's always equal to ma. I'm going to shoot that over here. We now know all our numbers. The F applied was 510. Subtract off the friction of 127.5, and that's equal to the m of 170 multiplied by the a. I didn't do any intermediate steps, I just know the final answer, but if you take 510 and subtract 127.5, you get a new number. Take that new number and divide by 170, the a value ends up being 2 1/4. And again, in meters per second squared. So the new point for this one is friction in the opposite direction turns into a subtraction when we're finding F net.